Hey everyone, this is Dr. Tracy, and this week we're talking about data storage formats. The announcement this week shows that there is a new project due, and only part A will be done this week because the other part's going to be done next week. So this week we're just going to focus on data storage formats. And the information that is covered in this chapter is bits and groups of bits, decimal, binary, hexadecimal, octal, and then examining how they are used in the mathematical equivalence of those numbers, what it means to be unsigned, and how that's incorporated into memory. So that's the stuff we talk about this week. Next week, we're going to be using C to explore those data formats and demonstrate data storage. There's an outline of the chapter of the first half, which is kind of the idea of what data storage formats are. And then there's an outline of the second part, which is going to deal with using C. So there is a discussion, which is Project 1 Part A this week. And in that discussion, you will complete these exercises, 2.2, 2.4, 2.6.8. So that means we're going back to the textbook. In our nice little free textbook here, ARM assembly language using Raspberry Pi, which we aren't, and we're also not using ARM assembly language yet. We'll start by talking about bits and groups of bits. You know, a computer doesn't know anything. Honestly, the only thing that a computer understands is on and off. And just like a light switch, it doesn't know anything more than the electricity is allowed to pass through in a certain place, which registers it of having a value that's positive, or it's not allowed to pass through a certain place that because of conductivity or because a gate was shut, and that registers it as having a value of negative or zero. So zeros and ones is everything to do with computers, and computers only think in zeros and ones, and nearly everything that makes up a computer has to deal with zeros and ones, and we call that binary. So it is clearly cumbersome because we are not prepared to think in terms of binary, since we think in terms of decimal. I'm going to open up Notepad here to demonstrate what I mean. We think in terms of decimal. Now, what decimal means is we have 10 digits for our counting system. And those digits are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. That's how we count. We have 10 possible digits, 0 included. And when we've used up all of our digits, and we can't count anymore because that's all the digits that we have that are available to us, what we do next is we put a 1 in the placeholder, saying we have used up all of our digits at least one time, and we're starting all over again. So we get 1 0, 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, 1 7, 1 8, and 1 9. And again, when we get done using up our digits once, we put another 1 in the tens place, meaning we've gone one time through our tens place, and now we've gone 2 times through. Now, this isn't any kind of a trick. I mean, not trick. This isn't any kind of anything you don't know. I'm just trying to explain a number system that you are familiar with using the same way that I will explain a number system that you aren't entirely familiar with. And that's binary. So here's what happens in binary. We have a 0 and we have a 1. There are only 2 digits in binary. So once we have used up the entirety of our digits, we have to put a 1 to hold our place, saying we've been through it one time, and then we start again. Now, we have used up all the digits again. Binary goes pretty quick. And since we only have 1s and 0s, we can't put a 2 anywhere. So what we do instead is put the 1 way out here. And we start all over again. Now we can say 1 0 1. 1 1 0, whoops, not a 9, a 0, thank you, and 1 1 1. Again, we have used up our placeholder. We can't do anything higher than a 1 since that's the highest digit that's possible in a binary system. No such thing as 2 and above. So again, we put a placeholder and move out to the left. And now we can start counting again using the 1 and 0s. Stop hitting 9, Tracy. There we go. 1 0, 1 0 1 1, 1 1 0 0, 1 1 0 1, 1 1 1 0, 1 1 1 1. And for all intents and purposes, that's going to give you a good idea of what binary is. Now, the equivalent of binary to decimal shows that 0 is equal to 0, 1 is equal to 1, but that's where the similarities stop. There is nothing beyond that. The 1 0 that's listed here, that's actually the decimal equivalent of 2. That leads me to my super funny joke. I have to type it because it's not as funny if I spell it out, because technically it says there's 2 types of people in this world, those that know binary and those that don't. But what's funny about it is that 1 0 is the representation of 2. Now, in computers, another magical number that you have to know is 8. And the reason why 8 is important is because we take the 1s and 0s and we call them bits. There's little tiny bus pathways the electricity can travel through, and it's either there or it's not, which makes it a 1 or a 0. But we don't just deal with 1s and 0s. We deal with 8 bits, which we call a byte. Having a byte means we have 8 possible combinations of 1s and 0s that can go together. So when we are dealing with counting by this number, we can also take into account that if in counting with decimal, this is the 1s place, this is the 10s place, and if we went beyond that, that would be the hundreds and then the thousands, because that's how we talk. In binary, this is the 1s place, the 2s place, the 4s place, and the 8s place. So this 1000 is a physical representation of 8 possible numbers. Now, the combinations that we can possibly make with 8 digits of 011, if I continued to count, you would find that it would go, next would be 10000, and then there would be 10001. And if I continued to count, you'd find that if I had a possibility of 8 digits, where the highest digit is 1 2 3 4 5 6 7 8, is that we would see that that's where we can hold a byte. And a byte contains a possible combinations of 256. So bytes don't count up quite as quickly as a decimal does, but that's where we get the numbers that can represent letters and characters and certain commands that are used within a computer itself. Going back to our bits and groups of bits, it also demonstrates another set of counting, which is hexadecimal. And the reason why hexadecimal is very important is because it's base 16. So if you understand decimal, base 10, and binary, which is base 2, then you'll see that hexadecimal is actually what is used far more often than either binary, which is cumbersome because it gets really big really quick, and decimal because that's our form of counting based on the fact that we have 10 fingers, 10 toes probably. But hexadecimal uses a combination of larger numbers in a smaller space, but still by using binary, because it is by 16. Now, the reason why that's important is because I can take very large numbers and make them very small by counting in binary, and it uses up less space in our reference. And this is something to learn as you start to learn architecture of how a computer works. So here's how it works. There is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 different characters in hexadecimal, starting with 0 and ending with F. And just like in decimal and just like in binary, if we wanted to count more, we have to put a placeholder and then start again. Oops. 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and after that comes 1A, 1A, 1B, 1C, 1D, 1E, and 1F. Now we have gone through every single possible combination that we could do with an hexadecimal using the placeholder of 1 in the 16th place. Now just notice that if in decimal that's the 10th place, in binary that's the 2's place, now we're dealing with the 16th place. So that means that whatever the value is, we're adding 16 to it. 1, 16, plus the numbers in the 1 place will be 2. We can show that 12 is equivalent to a decimal 18. And in here, 16 in the 1's place, 16 in the 1 in the 16th place, 8 in the 1's place basically means 16 plus 8 if we are converting that to decimal, which will make it 24. Now, because it gets smaller numbers, can be represented so big, we can take 2 characters, and the largest number that you can write with 2 characters in decimal would be 99, which is really of no use to us whatsoever. But the largest number that you can write in hexadecimal is FF, because after 1F comes 20, 21, 22, 23, and so forth until it gets to 2F, which would then take it to 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 3A, 3B, 3C, until it gets to 3F, which would then take us to 4F, 5F, 6F, 7F, 8F, 9F. And after 9F, we still keep going with the letters, so we see things like AF, AA, or no, let's start A0, A1, A2, A3, A4, and on down to AF. And then once we've gone through all of the A's, we have to go through all the B's. So B0 through BF. And then C0 through CF and D0 through DF. So the largest number that we can write in hexadecimal notation is FF. And what's interesting about FF is that represents 256 possible values. Okay, so back to what was important about 8 bits is that this in binary is a byte. A byte is representation of a location of memory, and a byte can store 256 possible combinations. But now we have something in common with that number 256. So that is why we see hexadecimal a lot. Now, octal you think might be in there because octal is base 8. It's going to function just like decimal and binary, where we're going to go 0, 1, 2, 3, 4, 5, 6, 7, stop, put a 1 in the 8th place, and start our count again. But octal never doesn't get to the 256 with any kind of savings because it is actually bigger than using decimal. So it gets complicated and a little bit more confusing. So that's my first video. I'm going to post another one, but that should just get you familiar with these counting systems.